Hello, welcome to my video series on calculus. Today we're going to be talking about real numbers, functions, and their graphs. In this series I'll be making extensive use of John Rogoski's Calculus. It's an excellent resource, and if you need a calculus book, this is the one to get. All of my exercises and their solutions will come from these books. Anyone who's interested can get a hold of me at this email address. This is brant@gmail.com. I'll probably be able to get back to you within a day or so. I'd like to begin with a brief description of what we're looking at doing. Calculus is a tool set that was derived from algebra by a bunch of very smart guys who come after a lot of very smart guys before them, and it allowed us to solve some problems that math really wasn't rigorous enough or wasn't complete enough to solve before they came along. And both main branches of calculus, differential calculus and integral calculus, are based on the concept of a limit. I wanted to show you briefly just sort of what we're talking about before we get into this here. The limit is a concept that allows us to describe the behavior of functions that we wouldn't be able to describe with algebra alone. If you recall from high school what a graph looks like and sort of more or less how it works, we'll be going over some of this stuff, so don't be worried yet if you don't understand what I'm talking about. But a function, let's just say that a function on this graph looks roughly like this. Well, a limit is a value, very generally, a limit is a value that one thing approaches. In this case, we would talk about the x-axis, the horizontal axis here, going on to the right without bound, going on to infinity, and how the shape of the function acts as x does that. And as we can see, this line right here crosses the y-axis at this point as x goes toward the right here. And we can see that the function is not, as far as we can see, right here, the function is not increasing beyond this line. We could use the concept of a limit to describe this behavior. We would say the limit as x goes to infinity of f of x, which is the function here, is the value that f of x approaches here. And we could also say that the limit as x approaches negative infinity, as x goes in the opposite direction without bound, of this function f of x approaches this other value that is down here below the x-axis. And this is useful not just for graphs and functions, although that's how we'll be describing it and using it here for a while. This is very useful for other things in nature, for electrical laws and in general the laws that seem to govern our universe. All of physics is based on calculus, and indeed calculus was developed to describe physical phenomena. So from the concept of the limit, we can start talking about things like differential calculus, which is where we concern ourselves with the rate that things change. You'll recall also from high school that a linear graph such as this, a linear relation between x and y, has a slope that's usually denoted by m, and it equals the difference or the change in y, that's what this Greek symbol delta means, this triangle, over the change in x. And what this tells us is that for every movement, every time we move on the x-axis to the right or left, y is going to change a certain amount. And this gives us the rate of change or the slope of this function. Well, with calculus, what we're able to do is unrestrain ourselves. We don't have to simply focus on linear relations anymore. We can have crazy looking functions like this, and we can talk meaningfully using the concept of a limit, and we'll get to the how and why later, but we can talk meaningfully about the rate of change at any given point on the graph of this function. So as you can see, I'm drawing these lines, and it's sort of telling that I'm drawing lines here because we're initially going to define this as the slope of a line that is tangent or barely touching the graph at any given point later on. But we'll get there. I wish someone had sort of told me when I started off in calculus what I was going to end up doing with it. So I wanted to give you a little bit of an idea here. Integral calculus, also using the concept of a limit, one of the first things we're going to do with integral calculus is we're going to determine the area under the curve of a sort of arbitrary function like this. And we're going to do that by imagining that there are these rectangles. We've known how to take the area of rectangles since probably middle school. We are going to imagine that there are these rectangles underneath the function. You can imagine that there are just lots and lots of these rectangles, and each of them have a certain width, and each of them have a certain height. And the height for each of these rectangles is roughly the height of the function f of x, and we'll talk about this notation today actually. But the height of the function and the width of these rectangles, where the function is just above each rectangle, gives us this the area of this rectangle. And if we imagine that w gets very, very, very small, so they're nearly infinitely thin, and then we add up a nearly infinite number of them, that what we can do is get a very close approximation of the area under this curve. So that's one of the first things we're going to be doing with integral calculus. Before we can get there, though, we need to talk about numbers. The set of numbers that we're going to concern ourselves with for the very most part in calculus are the real numbers, and they're usually denoted with this big fancy-looking R here. Sometimes in textbooks it'll just be a big bold R, but usually when it's written by hand in the math world, it looks something more like that. And real numbers are any numbers that can be expressed as a decimal expansion, and that may seem to you like that's just all the numbers, and it pretty much is, and it doesn't hurt to think about it that way for now. But some examples, 3/8 can be expressed as a finite, non-repeating decimal expansion, 0.375. An example of a repeating decimal that is still a real number is 1/7, where we get something to the effect of 0.142857, and then this series of decimals continues to repeat forever. So if I wanted to continue, I would write 142857 all over again, and it would go on forever like that. Still a real number. And then, of course, we have our all-time favorite, everybody's favorite, pi, which no matter how you slice it, we end up with a non-repeating, non-terminating decimal beginning with 3.14159, and it goes on forever. A subset of numbers that become very important in calculus are the integers, denoted by this big, similarly fancy Z, which stands for, I may be pronouncing it wrong, but Zahl, the German word for number. And if I've even got that right. R is also stands for a German word. I remember that from somewhere. And the integers are counting numbers. We could go, all the negative counting numbers, the ordinate numbers, the numbers that we use to discuss discrete things that have a beginning and end. And they would go on forever in both directions. Whole numbers are a little bit confusing. If you go look at them on Wikipedia, there are competing definitions. Rogoski uses the definition, and I will too, that the whole numbers are the counting numbers or the integers beginning with 0 and becoming increasingly positive Some definitions would exclude 0. Some definitions would include all of the integers, and it would be synonymous with integer. But in this case, we're going to begin with 0 and use whole numbers as the positive integers. A rational number is a number that can be expressed as one number, let's call it A, over another number B, and this means that it has a repeating or terminating decimal expansion. Pi is an irrational number because it is non-repeating, non-terminating. We also have in the irrational world, we have the square root of 2, for instance, which comes out to roughly 1.41, but which has a whole bunch of, well, an infinite number of decimals after that. I'm sorry, I keep right-clicking somehow, but yeah, I need to get better at my dots here as well. But and then we also have E, for instance, which also has a non-terminating, non-repeating decimal expansion, and we will talk about E and how it's defined a little bit later. But a rational number, keep in mind that any whole number or integer could be expressed this way. The integer 2, for instance, could be expressed as the number 2 over the number 1. Q, by the way, stands for the Italian word. I didn't even mention that. The set of all rational numbers is denoted Q, big fancy Q like this, and it stands for the Italian word for quotient, which starts with a Q. So there's that. Now, the absolute value of a number, as we probably recall, is the distance that number is from 0. So for instance, we have the integer 3 here on the number line, and we have -3 here. And both of these numbers have an absolute value of 3. Their distance, each of their distance, because you can't have a meaningful negative distance from 0. Your distance from 0 will always be positive, so what we get is that the negative square root of 3, the negative absolute value of 3 is equal to the positive absolute value of 3, or indeed, if we want to generalize this, the absolute value of any negative number is equal to the positive absolute value, or to the absolute value of that positive number. Let me say that again. It seems like I may have gotten it off. The absolute value of a negative number is equal to the absolute value of the same positive number. So the absolute value of -a is equal to the absolute value of a. They both have the same distance or magnitude from 0. When we start talking about vectors, we're going to see a form like this. We'll call these magnitude bars, and we'll be talking about magnitude, which is the same thing as the distance from the origin here, although we'll be talking about it on a 2-dimensional or 3-dimensional graph. It's also meaningful to talk about the distance between other arbitrary numbers and not just the distance to 0, and we can do this by taking a number A and a number B. And talk about the distance between these two numbers. And the way that we're going to find this, you'll remember from years past that you could, of course, just take the larger number and subtract the smaller number from it. But what's slightly less intuitive is that you could also take the absolute value of these numbers in either order and subtract them from each other. And what you get is the size of the distance between them, or the magnitude. And I will prove that to you, or show that to you rather, with, let's try the number a equals -3. Just a equals -3 and b equals 5. And we'll take, in this first case, we've got -3 minus 5. We're going to take the absolute value of that. And what we end up here with is -3 minus 5 is going to be -8. We'll take the absolute value of -8, which is just going to give us a positive distance of 8. And if we want to do this the other way, if we want to go b minus a, then we could get 5 minus -3, which is going to be inside the absolute value bars, which is going to be the absolute value of 5 minus a negative is 5 plus 3, which is 8. The absolute value of a positive 8 is still 8. These two things are the exact same. We're talking about the exact same thing when we use the absolute value bars like that. It's also important to talk about this triangle inequality, which simply states that the absolute value of the sum of two numbers a and b is always less than or equal to the sum of the absolute value of a and the absolute value of b. And this simply means on the number line that if we take a number a back here, and let's say that this is 0, and then we take a number b here at +3. So we've got a at -1 and b at +3. This means that if we add these two together and then take the absolute value of that number, then we would get b, which is 3, plus a, which is -1. 3 plus -1 is 2, and that's going to mean that the absolute value of our new number, the absolute value of 2, is 2, and that puts the absolute value of a plus b right here. Now, that is less than or equal to, is always less than or equal to the sum of the absolute value of a with the absolute value of b. And as we can see up here, the absolute value of a is its distance from 0. And since its actual value is -1, its distance from 0 is simply 1. And the absolute value of b is 3. And if we add those two together, then we get 3 plus 1, which is 4, which is going to be twice this distance, in this case from 0. And we get here the absolute value of a plus the absolute value of b. And that's right here. I would like to point out that if we moved a and a was positive, if we moved a up here to make it positive, let's say a is now 1 instead of -1, and b is here, and we wanted to take the absolute value of the sum of a and b. Well, we would first sum a and b. We would get 1 plus 3 equals 4, and then the absolute value of 4 would also be 4. It'd be up here. Well, if instead, so that's what the absolute value of a plus the absolute value of a plus b is. If instead we first took the absolute value of a and then took the absolute value of b and summed those together, we would get the absolute value of a is 1, the absolute value of b is 3, my apologies. We would add those together and we would once again get 4, which is the case where these two things are equal. But as you can see here, the absolute value of the sum in a and b can never be more than the absolute value of a summed with the absolute value of b. Now, something that's going to allow us to talk about all these concepts is our different notations for intervals, for sets of numbers. So right here on the left for all of these, we've got what's called interval notation, which tells us that we are talking about all the numbers which go from a number A to a number B, and these parentheses tell us whether A and B are included in that. An open parenthesis means that endpoint is not included, and that tells us it's an open interval. If there's a bracket, that tells us that the endpoint is included. In this case, A is included in the interval, B is not. So this would be all numbers between A and B, including A but not including B. Same thing for here on the B side. Now, on the right side of these equal signs, we've got what's called set notation, and it's a little more verbose. And how this is read is the set. The curly braces indicate a set of numbers. This is the set of all numbers x, such that A is less than x is less than B. And you can see here that this means exactly what this means. We are talking about all the numbers x in between A and B that do not include A and B, otherwise these would be less than or equal signs like they are down here. So this is the set of all numbers x such that A is less than x is less than B, or in other words, such that x is between A and B, like we've got it here in the parentheses. So if I wanted to draw this on the number line here, oh boy. If I wanted to draw this on the number line here, I would take A, and I would take B somewhere arbitrarily away. And I would indicate that I'm including all the numbers between them, but not A and B themselves. And I'm going to do that by drawing this parentheses directly on the number line. And then drawing on the number line where all my numbers could possibly be. X is in this range somewhere. For this next one, as you see, A is included this time. So what I'm going to do is I'm going to take my arbitrary number A and my arbitrary number B, and I'm going to include A this time. Just like I've got it here in interval notation, I'm going to draw a bracket right on the graph. But for B, I'm going to draw the same right parenthesis, and I'm going to draw all the numbers that x could be in between and including A. For this third one, I'm going to do the exact same thing, except A will not be included this time, and B will. As you see, once again, the set notation here is the set of all numbers x such that A is less than x, which is less than or equal to B. In the third case, we get more of we get a convention here. We never include infinity. Infinity is not an actual algebraic entity. It cannot in all cases be manipulated algebraically. And so one of the ways that we indicate this throughout our notation is that we never include infinity. We sort of admit that x can never reach infinity. This is actually a mistake right here. My apologies for that. We need to, this is not a less than or equals. This should be negative infinity is less than x is less than infinity. What this sort of indicates right here. And this interval is all of the number line. We would just color in the entire thing, because all the possible real numbers are all the values that x can take on, is what this means. We could also have gone from A to infinity, or from negative infinity to B, or from negative infinity to A, or anything along those lines that you would have liked. I would also like to point out that this this set notation here is short form. We assume that we're dealing with the real numbers x, because for most mathematical applications, that is what we will be dealing with. But if you wanted to be just a little more specific here, you could have said the set of all numbers x that belong to the real numbers, such that, and then listed your other rules for x here. So, a couple more number line things. If we wanted to talk about the set of numbers x which are always less than r, or the absolute value of x less than r rather, what we would be talking about is, let's call this 0. Every value of x, whether it's negative or positive, its distance from 0 will always be less than r. So r is some arbitrary distance, some arbitrary radius, if you want to think about this as a two-dimensional circle, where a circle is the set of all points, a certain distance from a specific point. Then a circle on a number line, a two-dimensional circle, would only include 2 points, and those 2 points would be a distance r from 0. And in this case, x is going to be all the numbers whose absolute values are less than r. So instead of just those 2 points, we're going to be including all the points between them, and because we've got a less than sign here rather than less than or equal to sign, we won't be including r itself. So we can say that this is r. R is this arbitrary radius, a distance r from 0. And this is an equal distance from 0 on the opposite side. This is negative r. This is the same distance in the opposite direction. And we're going to say that x can be all of the numbers whose absolute values are within a distance r from 0. So this interval, remembering our interval notation from the last slide, will look something very much like this. That is the set of all numbers x which make this inequality true. Now, it doesn't have to be 0. We could have done a distance r from any point c. What this means is that the distance from x to a number c will always be less than r. So the way this looks on a number line, and I'll show you a little more robustly here in a moment, but what we're going to have is a constant c in the middle replacing 0, and we'll have a number r, we'll have c plus r because r is a distance r from c. And then back here, we will have a distance c minus r. Now, this may not seem obvious from this right here, but I can show this to you. This symbol right here means equivalent to, and I'll be using it a lot, even more if my handwriting can get better, and maybe I can get a little bit quicker at this stuff. But this is equivalent to, let me go up here. I just want to show you that this real quick can be, anytime that you see a variable or an expression in absolute value bars on this side of an inequality like this. So what we have is the set of all numbers x that are less than this distance r. And we can see from here that what we really mean is that this is equivalent to the compound inequality. Negative r is always less than x is always less than r. And this almost jumps out at you from the number line here. You see that this solution set is all the numbers x that are between negative r and r, and this says that a little bit better than this does. We can do a very similar thing here. We can say that this value c minus r is less than c is less than c plus r, but we can do this algebraically without having to look at the number line, and we're going to do that by saying that this is equivalent to, just like we did above, we're going to say this is equivalent to negative r is less than the distance from x to c, the difference between x and c, which is less than r. Now, because we've got this negative here, we can get rid of these absolute value signs here. That's what changing the notation allows us to do. I'm going to fix this symbol. That's pretty terrible. Now, we can manipulate this algebraically. If you go back to your high school algebra class, we can add c to all three sections of this, and what we're going to see is that this is equivalent to, if we add c to these sides, then what we're going to get is a positive c and a negative r on this side, which is going to be c minus r, which is less than x, because we got rid of the c over here, which is less than c plus r, which is exactly what we see on the number line here. So this looks a whole lot more like this. And when you see this form, you know that you can sort of manipulate it in this fashion. And we're going to have an exercise that requires us to do precisely that. So the first thing that we're going to do is take this closed interval. It's closed because 7 and 13 are both included. The endpoints of this interval are both included. And we're going to describe it using set notation, using inequalities. So as you recall earlier, on the number line, that's the next example is what that is. As you recall, on the number line, this is the set of all numbers which include 7 and then go from 7 to 13. Well, how would we do this in set notation? That would, of course, be the set of all numbers x such that 7 is less than or equal to x, which is less than or equal to 13. We would close our bracket here, and that would be our answer. Now we can go to the second example. And this one's a little bit trickier. The book has us solve this by looking at a similar function, and I prefer methods that will work every time you use them. So what we're going to do is manipulate this algebraically to figure out where x lies on the number line here. So if you recall, what we can do when we see this notation is we can add the negative version of this number to the other side and take these magnitude bars away. So we're going to start off by going -4. The issue with this one compared to the ones we were looking at earlier is that this sign is in the opposite direction. This is going to tell us that -4 is more than 1/2 times x minus 3. And that is more than 4. And this is a little bit confusing because this value right here is less than -4, but more than 4. And that means that we're going to have two separate domains for x, two separate sets of numbers that x could be in, and then right in the middle there, or that this could be in, and right in the middle between those values is going to be a dead zone that x can't exist. So we're going to try and figure out exactly what that zone is, and we're going to expand our notation a little bit to describe it. So the first thing I'm going to do is add 3 to all three of these sides, and that's going to leave me with 1/2 x in the middle, which is going to be more than 7, which is going to be more than Negative 4 plus 3 is going to be negative 1. Now I just need to divide all 3 by 2, and this gives me x in the middle, which is going to be more than 14. 7 times 2 is 14, but it's going to be less than negative 2. Now, this is going to be the set of all numbers x. Now, what does this look like on the number line? Well, the range we're talking about has to do at least with, we'll call this 0. We'll call this negative 2. And we'll call this way up here 14. Now, we are talking about all numbers x that are less than negative 2. So all of these numbers back here, not including negative 2, of course, all of these numbers back here, and we're talking about all these numbers up here that are more than 14. How do we write this in interval notation? Well, we're going to introduce a new symbol called the union symbol, and we're going to have these two ranges that go to but do not include negative infinity. So negative 2, and negative 2 is not included either. And we're going to union this with this big U symbol with our upper range that does not include but begins at 14 and goes to positive infinity. And we're done. Now we're going to move on to graphing. We're adding a whole new dimension here by arranging two number lines perpendicularly to each other. Your x-axis, very similar to what we were looking at before, is a number line consisting of positive numbers to the right and negative numbers to the left of a 0 in the center, called the origin. And the y number line, the vertical number line, consisting of positive numbers going up and negative numbers going down from the origin. Any point on this graph consists of two coordinates, or consists of a coordinate pair, rather. Two ordinates, I believe, is what that's actually called. And the origin is located at the point 0, 0. Now that's 0 for the x and 0 for the y in alphabetical order. X, y, and that point's right here. If I wanted to find point 1, 4 on this graph, I would go to the right 1 because it's positive, and I'm going 1 in the x direction, and then positive 4 in the y direction brings me up here to this point. Similarly, if I wanted to go to point negative 2, 3, then I would go negative 2 in the x direction, which would be here, and then up 3 in the y direction, which would be this point right here. The quadrants, there are 4 of them, and they are determined, which quadrant you are in is determined by the sign of your coordinate pair numbers. If you were in quadrant 1, then you're going to have a positive x coordinate and a positive y coordinate. If you are in, let's just call this Q1, in Q2, you'll have a negative x coordinate and a positive y coordinate. in Q3, you've got a negative x-coordinate and a negative y-coordinate. And in Q4, you've got a positive x-coordinate and a negative y-coordinate. It always helped me to remember which quadrant was which because they're enumerated in a shape that looks like a C. Q1 here, Q2, Q3, and around to Q4 here. C for coordinate plane or for Cartesian coordinate plane. Always helped me when I was younger. The distance between 2 points on a graph finding the distance between 2 points on a graph is a fundamental skill, and we're going to use it when it comes time to start talking about derivatives. But we start with something that we probably remember from middle school, the Pythagorean theorem, which tells us that the hypotenuse of a right triangle, which is the longest side, is equal to both of its other sides squared and added together. And this is important because if we look at 2 points on a graph like this, we can see that the line between them we can call a hypotenuse, and then the difference between them in y we can call one of the sides, and the distance between them in x we can call the other one of the sides. So here, the only thing I've changed is instead of calling it c for the hypotenuse, I'm calling it d. So distance squared is equal to a squared plus b squared, where a and b are the sides. And you can see that I've defined a to be, if my points are defined to be point 1 is equal to x1, y1 right here, and point 2 is equal to x2, y2 right here, then the length of side A is going to be the difference in my two x's, my bigger x minus my smaller x, and the length of side B is going to be the upper y coordinate minus the lower y coordinate. So by the Pythagorean theorem, if d squared equals a squared plus b squared, I can replace a and b with these expressions, and I get d squared is equal to the difference between x coordinates squared plus the difference between y coordinates squared. And if I take the square root of each side, that's not good. If I take the square root of each side, like this, well, the square root of d squared is just d. It's actually plus or minus d, but negative distance is not meaningful when we're talking about distances on a graph. So what this becomes is simply d is equal to the positive square root of the difference in the x-coordinate squared plus the difference in the y-coordinate squared. And this works. You can try it. This works for any 2 points on the Cartesian coordinate planes, whether the points are positive or negative, no matter which quadrant they're in. This formula, fundamental to algebra and eventually to calculus, is called the distance formula, and it's one that you want to put on your formula sheet. The first thing we're going to do with the distance formula is derive the equation for a circle. Now we know that a circle is the set of all points a certain distance from the center of the circle, right? So what we've got here are 2 points. We've got the point A and B, and then we've got the arbitrary point x comma y, which could be any point on the coordinate plane, but we want it to be any point that is a distance r from A comma B. I hope that makes sense. Now, if we wanted to find the distance r between these 2 points, then we would use the distance formula. We would take the square root of the distance between this x-coordinate and this x-coordinate and squared plus the this y-coordinate minus this y-coordinate squared, and we would set that equal to our distance here, r. Well, if we square both sides, reversing what we did on the previous slide, what we get is x minus a squared plus y minus b squared equals the radius squared. And this is going to be our general equation for a circle. Anytime that you want to create a circle with its center at an x and y coordinate, then you would take your variables x and y, you would subtract respectively the x and y coordinate of the point that you're interested in from them, square them each, add them up, and then set them equal to the square of the radius that you want. So if I want a circle, for instance, if I want a circle with there we go. If I want a circle with a radius equal to 4 at point 2, comma, -1, fix that 2 up a little bit, then putting this in this equation, I'm fairly easily, I get x minus the x coordinate that I'm interested in, which is going to be 2. I square that, and I add that to y minus -1, and when you subtract a negative number, you may as well just add it, and square that, and I'm going to set that equal to the radius that I want, which is going to be 4, and I'm going to square the 4 and get 16. And if you go and plot this on a graph, every point that satisfies this equation, every point x and y that makes this equation true, will lie on a circle around the point 2, -1 with a radius of 4. Will lie on a circle that is a radius of 4 from this point. That brings us pretty close to function territory, although that's not a function, and we'll figure out why in a minute. Normally what a professor will do when you get an introduction to a function is they'll talk about a machine, and this machine they'll call f of x, and they'll talk about this machine as having an input and an output. And in this machine goes x, and out this machine comes y, or f of x, or more specifically y, which is equal to f of x. Now, this makes a lot of sense, and that is a pretty good metaphor for what we're doing here, but I wanted to go into a little more detail here about what we're actually doing. If we say that y is a function of x, or y is equal to f of x, then what we mean is that x drives y. The y value depends on x, and whatever you do to x, whatever operation you choose to perform on x, is what gives you y. So in this case, let's just take our x and do some stuff to it. Let's say I want the square root of x, and I want to add to this 4. And I want to square that whole thing. Well, all those things that I just did to x are the function. Those are what the function does to x. So I've got my function of x is equal to all of those, and my y value on my graph is equal to f of x. So I'm not going to graph this one because it could be a little bit tedious, but I just want to sort of illustrate that the function is what you're doing to x to get y. And in this case, once you have a function defined, then you don't even have to use x anymore. Whatever you put here is what you're doing the function to, or what you're operating on. So I could put a here, and I would get a function of a, and that would equal the square root of a plus 4 all squared. And if I wanted to perform this function on a discrete number, like let's say 4, then f of x ends up taking on a specific value, when x is equal to 4, you see I put 4 here where x was, setting x equal to 4, this is going to give me the square root of 4 plus 4 squared. And when I do my order of operations on that, I'm going to get 2 plus 4 on the inside. The square root of 4 is 2. 2 plus 4 is 6. I'm going to square that, and that's going to give me the square of 6, which is 36. So now I can say that when x equals 4, my apologies, y, or f of x, my function of x, equals 36. And if I want to write that ordered pair as it will appear on the graph later, then my x-coordinate will be 4, and my y-coordinate will be 36. Now if we take a simpler function than that, and we say f of x is equal to x squared, then it will be a little bit easier to illustrate it on the graph here. Let's take our graph and we'll do 1, 2, 3 ticks on the x-axis in either direction, and ideally we'd have 9 on the y, but we'll do 4. Then what I'm going to do is I'm going to look at all the x's on my x-axis, and I'm going to determine where the point would lie along the y-axis. So let's just go with 0 for right now, the origin. Then I put 0 in for x, and I get f of 0 is equal to 0 squared, which is equal to 0. So I've got a point at 0, 0. If I want to put 1 in to my function to see what I get out the other end, I gotta stop writing my 1's like that, honestly. Then I'm going to get 1 squared, which is just 1. So when x is 1, we're right here, and when x is 1, f of x, or y is 1, so we put it right there. F of 2 is going to be equal to 2 squared, which is 4. And we take a little jump here. You can see that this function is increasing more rapidly as we go to the right here in the x. So 1, 2, 3, 4. And the negative numbers, because when you square a negative number, its sign changes. Any number that you square, you're going to get a positive number. So it's going to be mirrored across the y-axis, because there is no negative 0 really, so we still have that point. F of negative 1 is going to be negative 1 squared, which is just 1 in the y-axis. So we get negative 1 on the x-axis and 1 on the y-axis. Negative 2 in the x-axis is still going to give us 4 in y. So we're just mirrored across the y-axis like this, and we sort of get this. The shape is becoming clear, and we get our essential parabola here, which I'm drawing not well at all. But so I hope that makes sense. Any function, and we're about to define what a function is and when something is not a function, we can graph this way. So when something is a function, let's draw an arbitrary function here. When something is a function, for any value x, there can only be one unique value y. So when x is at this mark right here, you see that there's only one y value that it correlates with. When x is this value here, there's only one y value that it can associate with. So the other thing is not true. If I wanted to this, for instance, is a function still, because for any value x, there is still only one value of y that it is associated with. Even though this y value right here occurs multiple times, even though this occurs multiple times, that's not true for any x value. Each x value will only have one y value associated with it. And this is how we know that something's a function. They like to talk about the vertical line test, which means that any vertical line that we draw through this graph will only pass through one point on the function. You see that this does not pass a complementary horizontal line test, because this horizontal line will pass through multiple points on the graph. But because a vertical line will pass through any point only once, this is definitely a function. Two other things that are really important to talk about here are the concept of roots and then domain and range. So a root of a function is any value of x for which the function value becomes 0. And that means that if we have a function like this sort of cubic looking function here, then the roots are where the function crosses the x-axis. Remember, the x-axis crosses the y-axis at y equals 0, and because f of x equals y, when f of x is 0, we have ourselves a root. For this particular function, we see that we have three roots where we're looking at it, and one of them is almost certainly 0. So if it wanted to, if it was asking for the root closest to the origin, for instance, or just one of the roots, you could say x equals 0 is one of the roots. And then these other two would be as well if we had more numerical information here. The other thing is domain and range. So let's take a look at a strange looking function here. Now, the domain, usually denoted D, or something approaching a D, of a function is all of the values of x for which the function is defined. Now, you'll notice that this function doesn't cross the y-axis. And as we know, the y-axis crosses the x-axis at x equals 0. So it appears that this function is not defined for x is equal to 0. So while it's defined for all other values of x as we go in either direction, it's not defined for that one, and that means the domain excludes x equals 0. So we would say in set notation that the domain equals the set of all numbers x such that x is not equal to 0. Now the range is the same concept for our y or f of x values. The range is all the values, we'll call it r for now, is all the values that the function can take on across its domain. So if the domain is all these values of x, then what is the range? It's all the values of y that the function can possibly be. And we can see that we've got sort of a similar situation here. That is, the y values get closer and closer to 0. They trail off and never quite reach it. It seems it's defined for the rest of them, though. So we could say the domain is equal to the set of all numbers y such that y is also not equal to 0. As simple as that. And when we start doing exercises here, there are a few specific things to watch out for when we're determining domains and ranges of functions. Now we're going to go to another example where it wants us to find the roots of this function. Now, remember that the roots of the function occur where the function value is equal to 0. So we're looking for where f of x, which we have a definition for up here, we're looking for where f of x becomes equal to 0. So what we'll do is set this equal to 0 and solve to find out which values of x make this thing equal 0. Well, I can see right away that I've got at least one x in each of these polynomial terms. So I'm going to factor those out, or factor one x out. I'll get x times x squared minus 2. Now, this remains equal to 0. Now, the only way that this thing can be equal to 0 is if, because this x is multiplied with this term x squared minus 2, is if either of these factors, this factor x and this factor x squared minus 2, are equal to 0. So I'll set them each equal to 0 independently of each other. Since this x would make the whole thing 0 if it were 0, we know that that's going to be a root. And since this is would make the whole thing 0 if it was equal to 0, I'll go ahead and set that equal to 0. And solve for x. Now this is equivalent. Remember this goofy symbol I can't draw very well on my trackpad. Is equal to, we'll add 2 to both sides. It's equivalent to x squared is equal to 2, which is further equivalent. Now I'm going to take the square root of both sides. And remember now, there are two numbers which when squared will give us 2. If I take the square root of both sides, what I'm going to get is the square root of 2, but it can be either the positive square root of 2 or the negative square root of 2. Both of those will give us a positive 2 when we square them. So it seems I found 3 roots, which makes sense because I've got a cubic function here. I've got roots at x equals a negative square root of 2, x equals 0, and x equals the square root of 2. Now, if you graph this function, and I encourage you to go to wolframalpha.com and just type in plot x cubed minus 2x, and you will see that this graph crosses the x-axis at negative square root of 2, 0, and square root of 2. Remember, square root of 2 is around 1.4-ish. Talk a little bit more about domain here and some of the things that we want to look out for. We will examine some graphs, I think, on here and maybe on Wolfram Alpha for these next couple. But for f of x equals x squared, you can sort of imagine that from negative infinity to infinity, you can pretty much put in any number here and get a valid value of f of x. As you go out, we remember our parabola from earlier. As you go out further in x, this thing will just get bigger and bigger and bigger and bigger. And as you go further out in the negative numbers, it will get bigger and bigger and bigger and bigger. And we say that the domain of this function is equal to the set of all numbers x such that, well, no, this domain is just equal to all the real numbers, isn't it? So we can just say the domain is all numbers x in the real numbers, and you don't even have to put this belongs to and are here because we assume that we are talking about real numbers unless otherwise stated. Our range, though, is a little bit different. You'll notice that no matter what value we put in of for x here, whether it's negative or positive, we always end up with a positive value for y or a positive value for f of x. So you would say here that our range is all real numbers y such that y is more than or equal to 0. And we sort of showed that earlier when we graphed this sucker. So that makes a lot of sense, right? Well, look at this guy down here. His domain's going to be a little bit more confusing. There is a number for which this thing becomes undefined. Remember, in algebra, we can't divide by 0. The universe will implode and we will all perish. So what we need to do is figure out when this denominator becomes 0, and we need to exclude that from our domain. So what we're going to do is take our denominator, which is x plus 1. We're going to set it equal to 0. We're going to solve for x, and we're going to exclude that value of x from our domain, like so. We'll subtract 1 from both sides. And now we know that x cannot equal this, so our domain is going to be all values of x such that x cannot equal -1. And if we go and look at this thing on Wolfram Alpha real quick, I'm still painting on my screen here. Plot 1 divided by x plus 1. Sure enough, right here at -1, we have what's called a vertical asymptote, where our function does not cross. Sort of a similar deal down here. When we're talking about real numbers, we want to ignore imaginary numbers, and that means that when we're talking about the domain of a radical function, an even radical function, we need to make sure that what's under here never becomes negative, because the square root of a negative number is imaginary. So what we need to do is use an inequality here. What I'll do is make sure that x minus 1, what's under the radicand here, is always more than or equal to 0. And I'll do that the same way. I'll solve this for x, and we'll get that x is always more than or equal to 1. And you'll see if we go and plot this thing, the square root of x minus 1, only a little lost here today. That it's sort of the same deal. We've got an imaginary part of this function that goes below. Well, that's the thing I didn't quite adequately describe here. Let me do that. The inequality that we ended up getting here, we said that x has to be more than or equal to 1, right? This is the domain is the set of all numbers x, such that this is the case. And if we go back and look at this thing, that's exactly what we've got here. We've got an imaginary part below that, and we need to ignore that if we want to do real math in the real world for the most part. So that makes plenty of sense, I think. Now, functions aren't the only things you can graph. We saw that earlier with our circle, which most definitely would not pass the vertical line test, and neither will this. So I just wanted to show you this. It's out of the textbook. This relation, 4y squared minus x to the third equals 3, does not pass the vertical line test, and therefore is not a function, but it still has a set of solutions, x and y, which form this graph here. Every point on this graph, 1, 1, 1, -1, whatever this is, each of these points satisfies this equation right there. These are going to become important later when we start doing implicit differentiation and some other fun calculus stuff. So I just wanted to show you that existed. Parity is another important concept, especially for some trig functions and function creation. And it's just for right now, it's a really good way to quickly plot functions. You remember our graph of y equals x squared, or f of x equals x squared, I should say. How we plotted half of that, and then we knew that all the negative numbers would end up spitting positive numbers out anyway, so we had this thing that did this sort of right here. And we knew that we had symmetry here, and that's all we had to do to graph it. This is an example of an even function. When you put in a negative value of x, what you get is the same function value as you would have if you had put in the positive value of x. Pretty simple to see that with x squared there, but it works. It's called even because the usually for a function that resembles this, we've got even powers on x, x to the fourth, x to the sixth, etc. When you start adding, we're going to look at translations and scaling, but when you start adding constants and multiplying this whole thing by other amounts, you can change its position on the graph. And if I were to move this over here, it would no longer be an even function because this would no longer be true for any values of x. Conversely, we've got odd functions, which are more like that cubic function we saw earlier, which was similar to y equals x cubed. And if we go and cube our x values, we get 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, which is way up here somewhere. That's 5. We'll call it right about there. But on the negative side, negative 1 cubed is negative 1 times negative 1, which is just 1 times negative 1 again, which is negative 1. So we start coming down here, and we end up at negative 8 as well. And what happens is instead of symmetry across the y-axis like we had with our even functions, we get symmetry across the origin. So here's an example of where we figure this out for a few different functions. Now, remember our definition of an even function was that for all values f of negative x, we got back the same value that we would get for f of x. Remember, I already told you that a function with an even exponent will resemble these, and this one doesn't have anything added to it or anything multiplying it, so it's a pretty safe bet that we're going to get that sort of behavior for a here. And we can go ahead and show that. Let's just take f of c, then we get f of c is going to equal c to the fourth power, right? Well, what about f of negative c? That'll equal negative c to the fourth power. Well, when we take this and we expand it, what we've got is negative c times negative c times negative c times negative c, which, when we multiply these two together, what we're going to get is positive c squared. And when we multiply that by negative c, we're going to get negative c to the third. And we multiply that by c again, we're going to get just positive c to the fourth, which is exactly what we got when we put in f of c instead of f of negative c. So we can rest easy knowing that this function is even. Now remember, for an odd function, we require that f of x, that f of negative x, when we put in a negative value of x, we're going to get negative f of x. In other words, we're going to get the opposite sign for our y value. So if we take this function right here and we put in f of negative c, well, let's start with f of c. What we're going to get is c to the negative first power, which is equal to 1 over c. But if we do this for negative c, what we're going to get is negative c to the negative first power, which is equal to 1 over negative c, or just negative 1 over c. So, as you see, this right here holds true for this, making this function odd. Now this function over here, x2 plus x, or x squared plus x, my bad, we're going to begin with the function f of x equals x squared, but we're going to do something to the function value. So if this was the original function value and we wanted to add the value of x to it, then wherever x is, let's say that x is 2 right here, we're going to add 2 more to that. Let's say that x is negative 2 over here, we're going to subtract 2 from that. Let's say that x is 3 over here, we're going to subtract 3 from that, add 3 to that. We're going to do that on both sides. So let's see real quick if it's, it seems to me that this may end up being odd, but let's find out. Let's start by assuming it's, let's start by assuming it might be even. Well, really, we don't have to assume much of anything, do we? F of c is equal to c squared plus c. Simple enough. What about f of negative c? F of negative c is going to be equal to negative c squared, which we know is the same thing as c squared, but we're going to be adding a negative c to this, or subtracting a c. Just do that. So we know that it's not even now because this is not the same value as this, but it might be odd. Let's see what negative f of c would be, and if these are equal, then this is an odd function. Well, that would equal negative c squared minus c. When we distribute this negative sign, what we're going to get is negative c squared plus c, which is not equal to this function. So what we have here for c is going to be neither even nor odd. This is just an exercise in sketching a graph here. But it might be helpful when we sketch it to determine if this graph is going to be even or odd. So let's check for that. F of c is going to equal 1 over c squared plus 1. So what about f of negative c? F of negative c is going to be 1 over negative c squared, which we know is the exact same thing as c squared, plus 1. So knowing that this graph is even, we only need to graph on one side of the y-axis or the other. So let's start with that. Let's go out just a measly 1-2 ticks. Now, at f of x, at f of 0, where x equals 0, we're going to get 1 over 0 plus 1 is just 1. and we'll put one up here. So we know that we have a point here. Well, what about 1? Well, that's going to be 1/2. That'll be right here. What about 2? That's going to be 1/3, roughly here. And I happen to know that this function continues to decrease like that, and I know that because as the denominator increases and the numerator stays the same, this function will get smaller and smaller quite quickly. So it's going to get closer and closer to the x-axis. But because I know that this graph is even, all I have to do is graph the right side, and then I can graph the exact same values on the left side. That is so terrible. And you can imagine what that would look like if I had better tools. But pretty good example of where even and odd helps you if you can prove it before you start graphing as you get at more complicated functions. Translation. So this is what I was starting to talk about. Changing the value of f of x by adding constants or multiplying it. And in this case, we know that if we take a function f of x and we say here are all the values that f of x can take on. Well, if I'm adding a value to f of x itself, if I've already got a function f of x and I want to add values to every value that f of x takes on, then I know that all I'm going to do is raise the height of this graph by a distance c. And that much is fairly evident, so we can go ahead and do this with a quadratic real quick. Now this distance between the two, of course, is c, because that's how much you're adding to the value of f of x. So if one function f of x equals x squared, we know pretty well what this graph looks like now. Where this is roughly 1, 2, -1, -2, and we go up like that. Well, what if I wanted to add 2 to this? Where would my new graph be? Well, all I would do is for every point on this graph, I would add 2 to it, and it would float above the x-axis and lose its only root at 0. This is valid for any function of the form f of x if you add a constant to it, or subtract a constant, then it just goes down that axis. Now, the phase shift, as this is sometimes called, is a little bit trickier. It does the exact same thing horizontally, except that it does it in the opposite direction of the sign. So if I have f of x equals x squared, and I have that same old graph. It looks something like this. And I add a phase shift to it. My new f of x is going to be f of x plus 2. Then instead of shifting horizontally to the right 2 units, I'm going to shift horizontally to the left 2 units. This new graph will be right here. Otherwise, unless I do something else to it, it will retain the exact same shape. And that's true of any function. When you have a function like we had earlier, y equals 1 over x plus 1, or I should say f of x. That notation is very helpful for when we're substituting values like this. So if I have f of x equals 1 over x plus 1, and now I want f of x plus 1, then this is going to equal 1 over x plus 1 plus 1. And this graph, whatever this graph looked like, we sort of looked at it on Wolfram Alpha earlier, will be shifted to the left 1 unit. It will be this exact same graph, but it will be shifted to the left 1 unit because of that phase shift that exists there. Simple example of that. Figure A is the graph of f of x equals x squared, like we were looking at earlier. The other figure is a horizontal and vertical shift of A. What is the equation of graph B? Well, if we look at this, we've got a vertical shift of -1, and we've got a phase shift of 1 going to the right. So our phase shift, we know we have to do, to get to the left, to get to the right, 1 unit like that, we're going to have to take f of x minus 1, remember, because it's opposite. And then to get down, we're going to have to do f of x minus 1. So whichever one we want to do first, we begin with f of x equals x squared. Well, we can go ahead and do f of x minus 1 squared, or f of x minus 1 equals of course, x minus 1 squared. And then we're going to, that was very silly. What I meant to do over here, and I'm very sorry to be confusing, was simply to subtract 1 from the value of f of x. So we're going to do that here. And because this is a new function, we don't need to call it f of x minus 1. We know that any value of x that we put in here, we want to go here. So we can just call this our new f of x. So this is the equation now of this graph. We could expand this out if we wanted to, and that would be x squared minus minus 2x plus 1. Minus 1 would get rid of that. So if we wanted to expand this, this is how it would expand out. And that would be the graph, the equation of the new graph. Similarly, what we were seeing earlier is scaling or dilation, which is where we multiply our f of x value by a constant, or we multiply our x value inside the function by a constant. And the effect that these each have is, in the first case, this is called an amplitude change, and it changes the vertical scale of the function. A positive increase in k will make the function taller, and a negative increase in k will, or a decrease in k will make the function shorter and more squatty. Similarly, scaling the x value within the function will, if it's a decrease in k, will make the function become expanded in the horizontal direction, and if it's an increase in k, it will make it become compressed in the vertical direction. I encourage you to play around with these. I'm not going to draw them out right now because they're going to be a lot more important when we start talking about trigonometric functions. But you could easily convince yourself that this will happen in all cases. That's it for today, guys. Thank you for sticking with me. I'm going to leave you with a couple of exercises, and I will post solutions to these, but I don't want to post them here because I want to give anyone who cares a chance to work them out without having the answers directly in front of them. So the first one is to find the equation of two different circles, each with the same center. One has a radius of 3, and one passes through the point 1, -1. For the second exercise, prove the triangle inequality by adding these two inequalities. And when you add these together, you'll sort of see where to go with that. But I'll post a solution, and until next time, thanks.